think this is a great tool because we are a large community, but we are all around the world, and then it is very difficult to meet all together. And this tool allows to do that very quickly and very easily for everybody. So I think that for us, for the astronomical community, this is really a wonderful tool, and we want to develop it. And well, we are trying, we are doing some tests, we are learning on how to work with this kind of tool. And then I think that we'll do better and better with the time. And for that reason, if you have any comment on the format of the meeting, please tell us, and we'll do our best to improve. Well, I would love that we have an interactive meeting, but the problem is that we are so many people around the table that it is quite difficult. So I think it's better that we all close the microphone, switch off the microphones. And if you have to ask, if you want to ask questions, and really you can do it, please do it by chat. And Olivier will look at the chat permanently. And if you have questions, Olivier will interrupt me, and maybe he can also give you the microphone. But the idea is that we do that by chat, and either Olivier interrupt me during the meeting, or we will ask the question at the end, well, depending on Olivier's decision. Okay. And last word for the introduction. We will talk about techniques today and how to calibrate the data with Demetra. So this is quite technical, but I want to insist that if we do technique, this is really to do science beyond. And what is important is that we use this technique to do science, and that we not just and only play with techniques. Well, even if techniques is just wonderful, but again, what is important is that we use all of that to do real observations and real discoveries and working together. Okay. Well, today we'll talk about the calibration with Demetra, the wavelength calibration with Demetra. We chose this topic because, in fact, we had several questions about the calibration, and this is one of the more technical steps in the data reduction with Demetra and in spectroscopy in general. And then I think it's interesting to just spend some time on understanding how works the calibration with Demetra and how to tune it to make it work really perfectly. Well, you will see that with Demetra, the wavelength calibration is really automatic, and normally we could stop the meeting in 3 minutes from now when I have demonstrated how it works normally. But I know that well, from time to time it doesn't work as it should. And this is the first part. So sometime we have to open the box and understand what happens. And also, in some special cases, you can have to adapt the parameters and the algorithm to your own needs. And especially, in fact, we decided to organize this meeting because, well, this is because of Robin Leadbeater, who is online. I hope. I think I've seen your name, Robin. And he told on the ARAS forum that well, he is not using Demetra yet, and mainly because he needs to have something very flexible with for the calibration. And I want to show you, Robin, tonight that the calibration calculation is very flexible in Demetra. I'm sure that you can use it to adapt it to your own need. Okay. Well, I've taken some notes. Well, and generally speaking, what is very important also is that even if this is fully automatic, it's very important that we all understand what we are doing with our data and how the data are processed and are used to calibrate the spectrum. Okay, so it's even if it is fully automatic and transparent, it's important that we understand what happens with the data. Okay, so perhaps I can switch to to sharing my screen. Can you confirm that you can see my screen? Olivier?
Yes, we do.
Okay. Yeah. Okay. Thank you, Christine. And so it's perfect. So I'm just running the Demetra software. So I do consider that you all understand the basics of Demetra. So you know how it works, or I know that most of you already used it. And in this meeting, I will just focus, or in this workshop, I will focus on this step, the calibration step here. So I use the demonstration images that are provided with Demetra. So it means that you can do exactly what I'm doing in real time with your own data. Okay, and I will work with the Vega star, because I know in my mind this is a reference star, and we can perfectly see the lines in the Vega star. So when we're talking about calibration, this is quite useful. Okay, so the normal usage of Demetra is really when I've taken all my images, when I've fulfilled all the baskets for my observation, I just go to the data reduction tab here. And when I click on the run button here, and all the steps go straight forward, and in few seconds we have the results at the bottom. Okay, so really when we talk about calibration, wavelength calibration in Demetra, this is very, very easy. Well, it's done, and you can see that the spectrum is calibrated, is already calibrated, and we display at the end of the processing, we display the Balmer lines just to have a quick view of the quality of the calibration. Okay, so this is the normal way. So this is why I told you that we could stop the meeting here. So how do we calibrate a spectrum in Demetra? That's just click on the button, and that's done. Okay. Now we'll spend a little bit more time on this operation, and try to understand what happens behind. First, if I go to this calibration step, I always have, you know, the principle in Demetra. You can double click on the image before, and double click on the image after the processing. And then in this case, for the calibration, you see that the difference is for the initial image, the scale, the horizontal scale axis is in pixels, okay, where after the calibration, the axis is given in wavelengths, okay, in physical wavelengths. So in fact, doing the calibration consists of, in fact, starting from the pixel position and give the matching wavelengths in physical units. Okay, so physical units, I mean angstroms or nanometers. Okay, I've a small graph here. I think you can see it. Olivier, that's okay? Okay.
Yes, it's okay,
okay.
yes.
This is just to show you very quickly. If you start from the pixel position here in the horizontal axis, you can have several measures, several points. In our case, it will be several emission lines, and you have to be able to calculate their matching wavelengths in such a way that after that, for each pixel in the horizontal axis, you will be able to say, okay, for these pixels, I just have to go to the curve and measure here the wavelengths, the matching wavelengths. Okay, so if you do that, you just have to know few points in the curve, and then after that you will fit well, usually a polynomial, or generally speaking, a dispersion law. In fact, in spectroscopy, the polynomial equation is perfect to do that. So to my knowledge, all the software use the same principle, and so in fact, fitting a polynomial is really common to all softwares. The only difference between different softwares are how do I collect these different points on my curve, okay, and how I can calculate this polynomial. If I take a polynomial of degree 2, I only need 3 points. And another way to say that is that if you have only 3 points, I can calculate there is one parabola that goes exactly through the 3 points. Okay. Now, usually, we have more than 3 points. And in fact, of course, if you have a lot of points, you cannot calculate a parabola that goes exactly through all these points. You have to do an estimation, and this is what we call a fit function. We try to calculate the closest polynomial that goes through these different points, okay? And the points are never perfectly aligned on the curve because we are doing technical measures, and all technical measures always have some discrepancies and tolerance and random position. Okay, so the real situation is this one. So you have different points, and you want to calculate the dispersion law that's allowed to calculate the wavelengths based on each pixel position. Something very important for me is that you see here I've drawn some points in the middle of the graph. And when you calculate the polynomial, you can extend the calculation on the two edges. And in fact, if I calculate a value within this area, we talk about interpolation, and this is generally speaking, this is quite precise because we have a lot of points, and we do a good approximation, and we always have some points not very far away from the one we want to measure. But if we want to extend this calculation, and this based on these values, I want to measure something here. This is what we call extrapolation. This is very dangerous because we have a good approximation of the polynomial here, but we don't know what happens outside of this band. So perhaps the curve should be here, or perhaps it should be here. So keep in mind that interpolating is something that is okay, that is good, it works fine. Extrapolating is always quite dangerous, okay? And you'll see that this is a problem in our case, of course, because we don't have all the lines we would dream to have. Okay, so I come back to the Windows, sorry, to the Demetra Windows. In fact, we have two different ways. So again, we have to find some couples of values, pixel versus wavelengths, at different position in our spectrum to do this calibration law. Okay, and when we have these couples of values, then the principle is always the same for all the software. In Demetra and in most of software, we always have the capability to calibrate manually, okay? And if I click on the manual position here, I can just click on the calibrate button, and in the bottom part of the screen, you have different values. And if I say, for instance, that I can use it very quickly, very simply, I just click in the middle of the lines, I just extend a little bit, and when I finish to extend, when I release the button on the mouse, then these small windows appear, and then I can enter the value. I don't remember exactly. I think this is something like 5852 or so, something like that, not minus. Okay, and then I can say it records. It will Demetra will measure as the exact position of the barycenter of this line. Okay, so this is why the value is with a high precision, and we give the wavelengths here. And I can do that with several lines. So for instance, I can do that for, oops, sorry, I don't really care. For instance, I don't know the value of this line, but in this case, I can give another value. And in this case, if I select, for instance, an order 1 polynomial, which I mean, it is a linear law, then I can compute the value, and Demetra will calculate based on this couple of values. It will measure the polynomial coefficients, parameters to fit these lines, okay? And that's it. In fact, you just have, if you want to do that, you can do that with several lines, as many lines as you want, of course. You can add as many lines as you want. And you can also select the order of your polynomial. Well, usually we work with the polynomial too. Okay, and of course, to work with the polynomial too, we need at least 4 points in the spectrum. Okay, and so this is the way to process manually. And when you have done that, you can just click on validate. It will send all the values that are calculated here. It will send the values here, and then I can run my calculation here, and I will see the results of the calculation. And in this case, I can see, well, here I have the position of H alpha is 6,834 angstrom, which is not the real value, because I just put dummy values in my calculation. Okay, but this is the way to do it manually. So you can do it manually, and it works. I know why not? Now, what is much more important, I think, is to look at the automatic process. Okay, and with that automatic process, in this case, I just have to click on the run button, and I see immediately the result of the curve. And I see that the Balmer lines are properly positioned. And well, by the way, if I click before, I have the pixel scale, and there is no reference because I have no idea of what are the wavelengths. But once I have the wavelengths conversion, then I can draw the color band in the bottom part of the graph, because now I know what are the actual wavelengths. Okay, and so now how works, well, this is magic, and now we have to understand what happens. Okay, when I am in the automatic mode here, I can click on the calibrate button, and this will open a new window, which is the calibration tool. So I insist, this tool, it is quite rich, quite complex, but in normal condition, you never have to go to this tool. Okay, so really the idea of Demetra is that we do something very simple, and we just have to click on the button, and that's done. Okay.
François, just
oui.
I have a question from David. How do you erase a line if a mistake was made?
Oh, you mean in the manual? I guess in the manual process.
Yes, just before you go. Yes, I think.
I think that I can remove this line and just remove the line here. No, up. No, it's not. I don't know. Good question. I don't know. Or perhaps edit. What mean? Oh, I don't have the answer. I don't know if Nicola is around and he can tell me.
Yes, Nicola is online.
Okay, so and Nicola, do you remember? Or?
Yes, hello everybody. Sorry for being late. Yes, François, but I'm just I'm in since 30 seconds, so I don't know.
What is the question? The question,
yes.
do you know how to remove a line here in the manual calibration?
To not use it? Ah,
yep.
Remove? Yes.
Yep.
If you click on the remove button, it doesn't work? Remove line?
No, it removed the bottom line, but not this one.
Yeah, but okay, but you can't. If you want to don't use the line, you just have to uncheck the box. But
okay. Okay, but I cannot. Okay, so I cannot check it and do the calculation. But okay. Well, the good point. We'll correct it.
Yes, removing the line is something I did very few time ago.
I would prefer if all the questions that you ask are not pointing to some bugs. Okay. This is not the idea, the purpose of the tonight meeting. Anyway, I'm kidding. We will correct that, of course, and of course we must be able to remove any line, and it should be using this remove line button. Okay. Well, I continue. I go back to my automatic tool, and I go to this calibration window. Okay. Olivier, that's okay. There is no other questions.
No more questions.
Okay. Okay. So now we see in this tool, again, this is a quite rich tool, and in normal conditions, you don't have to go there. But the principle here is that we have the two steps. The two steps to detect, to do the identification of the lines. Here, I have two buttons, two radio buttons. I have the detection step and the identification step, okay? And it is made really in two times. The first one, detection, it will detect all the lines that are present in the calibration spectrum, okay? So you can see that there is a huge number of lines. And if I zoom in this image, oops, sorry. If I zoom in this image, sorry, I will fit again. If I zoom in the image, then you can see that there is really a lot of line detected. And even banded lines like this one, you can see that we detect the two lines, the two different lines. Okay, so this is something well, impressive, and all these lines are detected through the parameters that are in the top right corner here. So we have different parameters. Maybe I will not go to too much in detail to these parameters, but if you have questions, we can go in detail. And in fact, we define a threshold. Well, first we remove the continuum of the background, in fact, of the spectrum, so you can see the continuous line here. So we have we remove this value, and I can I think I can display can I display it? Well, no, well, I will not spend too much time on that. We are able to define a threshold based on the noise of the signal in the background of the spectrum, okay? And then we define a threshold, and all the lines that are above this threshold are considered as a line. And in fact, we always consider the distance between the base of the line and the top of the line. So it means that even in this case, when we go down, we can restart counting for a new line where it goes up. Okay, so this is the way we go through all the spectrum, and we detect all the lines. And at the end, we keep only a certain number of lines and the most powerful lines. So the lines that have the highest energy, so the biggest surface below the curve. Okay, so in this case we have limited to 80 lines, so we can change this parameter, of course, but the idea is that we do a selection and we don't keep the smallest very small lines that are mixed with the background. Okay, in this list here also you have something which is very important. So here you have, of course, the list of all the detected lines. Okay, and here on the right you have a list of reference lines. Okay, so these lines are well known to be these are really known as being part of the well, I think I can show it here. When I look at the neon argon spectrum, we have some lines that are well known, okay? And the most important lines here are considered as reference lines, okay? And these reference lines are listed here. And this list is very critical because this is the list we use to make the automatic calibration. And in fact, based on this list, well, by the way, you can access to the reference documents by clicking on this button here, the show reference document. Okay, so you can have direct access to this document, and maybe we have to improve this document. But, anyway, it already exists in this format, and that's not so bad. Okay, here we have the list of the reference line, and in fact, Demetra will look for the best matching between all the possible combinations of all the detected lines here and this list of lines. Okay, so this is a complex calculation because it will test a lot of, well, it is thousands of combinations, okay, and it will keep the best one at the end, and the best one is the one that has the lowest error mass, okay. By the way, if I go back to my drawing here, the RMS is quite something very simple. The RMS, we just, when we have the best fit for all these points, and we go to the equation of this parabola, the RMS is just the average, or the sum, not the average, it's the average, the sum, sorry, of the distance between each point and the curve, okay? So we just measure the distance here, and we add all the measures, and then the total RMS at the end is the total RMS, okay? And of course, we understand that the lower is the RMS, the better is the solution, okay? And by the way, if I go back to the initial curve, if I have only 3 points, in this case, the RMS will be 0 because we'll have a perfectly matching parabola for these 3 points. Okay, so again, the criteria of the I'm going back to the Demetra. This criteria is very important, and then for each combination, in fact we try to we consider that for instance this line is this one, this line is this one, and for instance this one is this one on the right, and then we do the calculation, and based on this hypothesis, then we calculate a matching parabola, and then we calculate the total RMS with this combination. So we have a lot of combinations, and at the end, we just keep the best one, okay? So this is not exactly the case, because for a quick calculation, we have a first pass, which consider that we have a linear dispersion, and after that, we keep the best 120 combinations that are here in this parameter. I hope that you can see my mouse. And in this case, so we keep the best 120 combinations. And for these 120 combinations, we will recalculate the exact value with the second or third degrees polynomial, okay? And then we redo the calculation, and then we select the best one. Okay, so this is the way we consider we have this matching. And when it is done, so after this identification, when I click here, I see the result of this calculation. And here I can see exactly what are the lines that have been selected. And when I see that all the lines that are selected are matching with very clear and high lines, I know that the calibration is correct, okay? So this is why it works, and this is very robust because you have a high number of lines. So the probability that you can find a false solution with a better combination than the real solution is almost 0. Okay, so of course you have to have enough lines. If you're in your list, in your reference list here, you have only 3 or 4 or 5 lines, there is a very high risk that along all these lines, you may have a combination with a very good result, which is absolutely not the right combination. But as soon as you have a high number of lines, then it becomes really very, very probable that you can find the right result. Okay, so now there is one condition for which the algorithm calculation works, is that all the reference lines here, all the theoretical lines here, must be detected in the spectrum. Okay, if you have one line which is not detected because it is too faint, and maybe your spectroscope is not focused enough, and if the line is below the threshold, then it is not detected. And in this case, Demetra will find a solution with a missing line, and then for sure it will probably find a solution, but the RMS will be poor, will be very bad, and then either it will fail or it will go to a totally false combination. okay? So the real condition to make it work is that all the lines are clean and you are sure that they are properly detected in your spectrum. See, this is the only condition. Okay, so a very simple way to see if there is a problem somewhere is just to look. For instance, I can go to this line here, the 5,852 lines. Here at this position, if I look at where is this line, well, I selected because this is the big one here in the middle of the spectrum, okay? And then I know that this is this line. So in this case, I can see that it is properly detected. If I zoom on it, I can see that it is properly detected, okay? At the position, pixel position, 902 in this case, okay? So I can check for all the lines, and if your calibration fails, this is probably, very probably, because one of the lines here is not detected in your spectrum. So the simple way is to just to remove the line from the list, but the better way is to understand why it is not detected. So this is very strange, because all the lines that we have put here are the lines that are really present in the calibration of the LP spectroscope. I didn't mention that at the beginning, of course, but I'm working with an LP data in this case. Okay, and by the way, before I forgot, this is exactly the same process with the eShell or with the LISA spectroscope, and the LISA and eShell versions of Demetra. Well, for the eShell, it's a little bit more complex because you have many orders, so you do many times the same calculation, but the principle is exactly the same. So you can really do the same with the other instrument. Okay. And well, what else? Well, you have to probably to edit or to remove some lines. And now, so this is the part, I guess, for Robin. You can, of course, you can edit this reference line list here, and you can do what you want. So you can remove, add lines. If I want to add a line at, if I would have a line at 3,700 lines, it would be added here. I can remove one of the line and so on. And I can even create a new list. Okay, so I can save a new list with another name and say, okay, I save it as a new list on the disk, and then I can do different tests with different combinations. Okay, so in normal case, if you are using an LP with the standard calibration module, with the argon and neon lamp and so on, it should work. Really, it should work. If it doesn't work, maybe this is because your spectrum is not focused enough or something like that, but it is very highly probable that you can do it. Now, if you want to do that with another instrument, another spectroscope, or any, or if you have any specificity in your system, or if you want to better focus on some part of your spectrum or things like that, you can edit this list and you can do what you want with this list. Okay.
François, I have a question from Gavin.
Yep.
So I just, he tell me that I have seen suggestions that LP should run with polynomial degree 3. If we have many more images, should we raise that to 4 or not? Or should we always stick to polynomial of degree 3?
The polynomial degree for me is it doesn't depend on the number of images, and it even don't depend on the number of lines you have in your reference list, or the line that you want to use to calculate the polynomial. The polynomial degree only depends on what is the best curve that fits the dispersion of the LP in this case. Okay, so it's really related to the physics and to the optics. Okay, in fact, the fact that we consider that the spectrum, the dispersion law for an LP is not linear. This is mainly because of the prism that we have in the LP that makes some non-linearity. Okay, and this is the reason for that. So now the only question, do we use an order 3 or 4, only depends on what is the best for matching to this optics and optical dispersion. And well, my experience say that the difference between degree 3 and 4 is so small and so minimal. So for me, there is no interest to go above degree 4. But again, here, I'm talking from my technical experience. Maybe there are some observers that may have another opinion regarding really a scientific values. Okay, I hope I've answered the question. Well, I think I've almost finished here. Something important also is to see that when if we change any parameter here, for instance, I can. I don't have the control anymore. Oh, no, this is because the list is not closed. Okay. If I change one value here, I have to click on the set button to record this value. And then I have to click on the run button to rerun the calculation. Okay. So in this case, the result is exactly the same. Okay. I can change if I do, if I put 50 as a threshold here, I don't know what is the value that will work, but it is probably, no, even with 50 still works. I guess that there is a value for which it will not work. Yes, in this case, we are on the case where you can see the threshold in the bottom part. This is the purple line here. And then the threshold is so high now that I've detected very few lines, okay? And within these few lines, I don't have all the reference line that I'm expecting. So in this case, Demetra cannot find a proper solution that match this system. Okay, this is just to show you that this value, I put back the original values, depending on how you select the parameters here, you will succeed or not in the calibration. By the way, we know that by experience, a value for the RMS, this is really the figure to look at, a value below 0.5 for the LP, and this is in angstroms, is something we consider okay. Very often we are below this value, we can do better. And by the way, I am sure that in fact we could work on this list and improve the reference lines list and add more lines, because you can see that we detect much more lines that we have in the list here. So now, based on the algorithm that we have in Demetra today, I think that we could really rework on this line list to improve the system. Now there is also...
Sorry, François, I have two questions. First, a comment from Woody. Besides focus of the LP, also if the near-argon line does not show up strong enough, maybe the exposure time needs to be increased. So that's the first comment from Woody.
That's very good. Okay, thank you. Mm-hmm.
And a question from Jörg. Does it help improve the quality of calibration by stacking several calibration images?
So that's a good question. You know that when well, the short answer is in my mind. When we are stacking images, this is to detect, to improve the signal to noise ratio. Okay, and when we are looking at faint emission lines in the spectrum, then really we are looking to improving we are trying to improve the signal to noise ratio, the SNR. But when you look at this, in fact, you can see that the lines have a good SNR. I mean, naturally. Okay, so you have a good SNR in these images. So you can clearly see the lines. The emission lines, because the intensity of the lines themselves is very high compared to the background. So you even on only one image, you have a good signal to noise ratio. Okay, so you don't really have to stack images, but what is important is to have enough exposure time. And of course, well, I think you can much better improve the signal to noise ratio by increasing the exposure time than by stacking a lot of images. Okay, I hope I'm clear.
A comment
So,
from sorry,
and just to finish, sorry, Olivier,
okay.
just to finish on this point, what I usually do on my side is I take only 2 or 3 calibration images with the right exposure time, and I take a few of them just in case of we have a cosmic ray on one of the spectrum that would break totally the image. Okay, so this is just to avoid that.
Comment from Robin. I think stacking calibration images can work better than long exposure when they are very strong on weak line, as it avoid saturation. That's a comment from Robin. And I have a question from Sashi. How does the automatic method determine the threshold?
Well, the threshold, in fact, the threshold is defined by a value here, and this value is a number of sigmas, and the sigmas is the dispersion of the points in the background of the spectrum. Okay, and in fact, we have figures here. We take sections of 80 pixels here. So we cut the spectrum in 80 section of 80 pixels. And for each of them, we consider that we do an histogram of all the pixels, all the value in this 80 pixels range. And we consider that half, so 50%, 0.5 here, the back rate, half of the pixels are in the background. So we consider in such a spectrum that the background is made of half of the pixels. And then based on that, with the 50% lowest values in these sections, then we consider that we are in the background, and then we measure the dispersion, so the RMS of the background itself. And then we multiply this value by, in this case, by 7. So this is why we have something that really the threshold comes from the image itself with the coefficients, while 7 sigmas means that we are far above the noise. Okay, I hope I answered the question. So, well, by the way, I think I finished. At the end, I just have to do that, so I can really edit the list. So I'm thinking to Robin when I do that. So you can really do your own list with your own application and your own instrument and even your own scientific target, and then you can really play with that. And again, the goal of this tool is just to collect some couples of values, pixel wavelengths, pixel wavelengths. And the more we have, the better it is. And of course, in this case, the idea is that we even don't ask the user, well, this specific line at which wavelength it is, and so on. You don't have to know the system, because in fact, the secret of Demetra is in this list, which is of course totally transparent, and you can edit yourself. But the secret is here. So this is the most important lines in the argon and neon spectrum. So based on that, Demetra can recognize the pattern, and then it does automatically the calibration.
Another question from Robin. He says, I see the standard LP lines list stop at around 4,100 angstrom. How good is the fit below that?
Very good question, of course. Thank you, Robin. And of course, this is important. I told you that this is very important to not extrapolate. And for sure, when we see that, when we see this spectrum, I see the identification, and when I fit here, I see that this first line here is here, and we still have some signal here. And then, of course, when we extrapolate here, then we in fact, what will happen is that we will extrapolate. So we calculate the polynomial based on all the values we have, and then we extrapolate. And as I told you, extrapolating is quite dangerous, of course. So this is, and the only way to correct this and to improve this is to find other lines in this list. And to be honest, we should all these lines here are detected. If I look at the detection position, I see that all these lines are detected. So if we can define the actual wavelengths of this line, we should add them in the list. Okay, but the problem is that these lines are quite bended and so on. And in fact, we never took the time to do it. And well, and that's stupid. But when I look at the reference list here, well, it's a pity because it starts at this value. So it means that we have to do some library work to find the other value. But if we can find this value precisely, of course, we should add them in the list. And by the way, to finish with this question, when I look at that and when I look at the result here, I can see that you have some gap here. Sorry, if I zoom here in this part of the spectrum, you can see the difference. You can see the effect of the extrapolation. Okay, and to be honest, when we have seen that the first time, so we thought it was a very good idea to display the Balmer lines. To display Balmer lines to see at the end what is the result of the calibration. Okay, and in fact, very quickly we saw, we see that the precision is not that good in this area. Okay, and we hesitate. Well, no, in fact, we didn't hesitate it, but we said that we prefer to show that there is some discrepancy here instead of masking the thing and say, well, it's perfect, it's just perfect. Okay, what I can say is that the algorithm is correct, so the calculation is correct, but we are missing some data in this part of the line. Okay, so I know that for some cases, IZ software, for instance, uses, because the problem is that we don't have lines, and in fact, we have some lines in this part of the spectrum, but they are not bright enough, and the sensor is not sensitive enough to show them. Okay, and the point is that we have a lot of energy in the stars as these wavelengths, and we have this domain, this wavelength domain is useful to observe the stars, but we don't have the reference line with our instruments. And one of the way, of course, is to use a star itself and use especially the Balmer lines here to do this calculation. Well, at the moment, in Demetra, we don't have this feature. And well, depending on your need and depending on what we have to do, maybe we can add it, of course. And this will make the system a little bit more complex, but this is technically feasible. Okay. I think that's it. Just something important to me is again the normal way to process is just to click on the button here, and that's it, and do it automatically. Just if you want to check that your calibration is correct in normal conditions, well, first when I run the whole process, I see immediately the full result of the calculation. Just a few seconds. Okay, here it is. So I have, at the end of the process, I see the Balmer lines. So in this case, this is very easy because this is a hot star. In some stars, you don't see easily the Balmer lines, but in this example, it is very clear. But you can always go to the calibration step and check that the wavelength calibration is okay. So this is very similar to the what we saw just before, but you can also double click on the calibration spectrum and see the results of the identification. So here again, you can see that the detection works perfectly fine because you can see all the lines here. So even if you don't open the calibration tool, you can check very quickly that the calibration was fine. Okay. Hey, I think that's it.
Look, François, if you look the chat, you have a question from Shin. I just let you read this question.
So I have to find the chat. well, maybe I will stop sharing my screen. Okay. So this is wow, there is a lot of comments that I didn't see. Oh, one thing that we have found useful is after validating the calibration, run calibrate on the calibration image itself and to look at the fit of all lines, including those those weren't used. Yeah, exactly. This is well, this is not a question. Maybe tell me which one you want me to reply. Anyway, yes, the looking at the result, the calibration result is something and very useful in a day-to-day conditions, just to check that everything is okay. And also something important that I didn't tell you, but maybe when you observe the first time with your ALPI, maybe you may have some calibration issue because of what we have seen, so either focusing or the line detections or things like that. But for sure, once you have tuned the system, once you have found the right line set and the right parameters, which will be probably very, very close to the default value, then it will never change. Okay, yeah, really, it will never change. So, Olivier, you tell me which one.
No more question. Just Hugh says that he used the line at 3946.1 angstrom as well.
Okay, perfect. You just have to know it where it is, and okay, perfect. Hey, we can try to do it. So 3946. If let me share again my screen. So if I open the box, I go there. If I add 39.1, I add it. I try. I don't know what will happen. Let's try. And oops, sorry, I have to remove that. Run. No, in this case, this value cannot work. Okay, so it means that with these conditions, so I don't know which one it is, but in the conditions of this this value, it doesn't work. And maybe this is because I need a more precise value than the 0.1 here. Well, I don't know exactly, but what I know here is that if I just add this line, that's not enough. I cannot find it in the system. Okay. Any other questions? I have to recover. Again, I stop sharing. Oh, this is a good question. From Shashi. In the case of Comet, we could use the line, the CN line. This is not totally true because these lines, the fact that the line is present in a comet doesn't really care for the calibration, because for the calibration, we only use the lines that are in the calibration spectrum. Okay, so really we don't use the features in the star spectrum, but we use the features in the calibration spectrum. So in this case, if we could have a system that is using some lines in the star spectrum, maybe we could do that. But this is not the way it works today, and again, I think that there is no real reason to change it soon and to make it more complex. Okay. Well, Olivier, I will not read all the questions. Or
no,
there's something. Maybe I see a question from Christine here. Could you explain why you have to do a calibration spectrum for each observation? In fact, this is not really for each observation, but this is at least for the ALPI. This is at least one time during the night. And well, in fact, it depends on the calibration precision you need in your case. But for sure, as long as you do not change anything in your instruments, in fact, the calibration dispersion, with the calibration spectrum will never change. So you can keep it for a long time. But as soon as you change anything in your hardware, you move the camera, you remove the camera, you remove the spectroscope from the telescope and so on. In this case, there is a risk that the calibration spectrum will not go at the same place on the sensor. Okay, and in this case, you have to redo your calibration images. So for me, a very basic rule is to do at least one spectrum at the beginning of the night. And depending on what you are doing, if you really want to have a very high precision, which can be the case, for instance, if you are working with the RS or with the HL, it can be better to do calibration images much more often. Okay, but again, you have to think if you are you looking for very accurate the values in the calibration for your scientific objective, or are you just looking for identifying some lines and so on? So it really depends on what you are looking for. But generally speaking, DLP is a very stable instrument, and from the beginning of the night to the end of the night, if you don't change anything on the instrument, it will be stable.
Thank you.
Okay.
Thank you. Because I've got libraries of darks and so on, and I should think I could do the same with calibration at -10 degrees or 0 degrees.
I understand the point. Of course, for the dark, mainly for the dark and also for the bias image, we have the libraries because these images are long to make and to take. But you have to really to understand that the bias image and the dark image only depends on the chip, on the CCD chip. Okay, it doesn't depend on the optic in front of the CCD. The calibration image really depends on how the optic will manufacture, will print the spectrum on the sensor. And for this, it really depends. This is not the same as for the dark. It really depends on the whole equipment. Okay.
I have a question from Woody. Who tell me, do you think Demetra will be able to process LARES-free data in the future?
Oh, of course, yes. All depends on what you mean by future. The point is very simple. When we switch from one instrument to the other, the general process is almost always the same. So you can see that, well, for the people who used the beta version of the LISA Demetra for LISA, the process is exactly the same. And the only change is this reference line list, which differ from the LP to the LISA. The point is that in this case, we can recognize the pattern, and we have this automatic algorithm. In the case of LARES-3, there are two major problems. The first one is that we only have few lines. And really, if we only have 2, 3, 4 lines in the spectrum, it is not enough to apply this algorithm. We have to find another way to do it, okay? Because if you have too small number of lines, you cannot recognize a pattern. In fact, there is too many possibilities that you find a false solution. And the second problem with the LARES-3 is that you can rotate the grating, and then you never know exactly where you are in the spectrum. And this makes the thing very complex because, again, I told you that what is important in the algorithm that we have today, we have to be sure that all the reference lines are detected. And if we want to put all the reference line, all the lines that are potentially accessible to the LARES, and in this case, that for a given exposure of the LARES, we only have few lines, and then we'll miss a lot of reference lines. So by construction, this algorithm doesn't work for the RS3. So it means that we have to do something else. And I know that there is a lot of demands for that, and I hope that we do it. But well, this is just a question of time. We will have to use another way to do the calibration. And well, the other way is probably something very, very close to what ISIS is doing, is just asking the user to help Demetra and say, well, this line is at this position, you know. But well, this is just to be done. And again, because we're working on the UVEX spectroscope, which is a new instrument, and we will also have the grating that can rotate. And then I think that we'll face to almost the same problem. So in my mind, I want that we spend some time to work on the UVEX situation, and I hope that we will be able at the end to extend what we have done for the UVEX to the RS3. But well, I cannot promise. This is just a question of time and well, mainly a question of time and energy and money and so on. But I know there is a high demand for the RS3. Is it possible to ask Robin, if you are still around, if this you did learn things, and does it reply your need, or does it is it okay for you, or you still miss something to use Demetra today?
Hi, Francois, can you hear me?
Yeah, I can hear you.
Great.
Wonderful.
Yeah, that algorithm is very interesting, the ability to find lines even when you don't tell it the position of any line. Mm-hmm. I think you're right. If you give Demetra one line position, like ISIS does, that should make it work okay with the LIRES, for example.
Yes, sure.
I think I'm going to have to try it and test it out on some of the different configurations I have to see how it will work. For example, with the Alpi 200, where I've put the different GRISM in, a lot of the lines in the NEAR spectrum are blended at that low resolution. So it might be difficult to find lines. And ISIS does not work. I cannot get ISIS to work on the Alpi 200 spectra.
I'm almost sure that it should work, but of course you have to review the list and to identify in your Alpi 200 spectrum all the lines that are useful. But if you can find, I would say, you can find 7 lines in your spectrum, I think it will work.
Okay, thanks, Francois. It's been really interesting, and I think it's quite an innovative way of tackling a difficult problem.
Well, by the way, regarding the innovative approach, I know that there is, I think Mathieu Lelin is online also, and on his side is working with some students, but he's working to use some artificial intelligence to do this detection of the lines. So this is another approach, and I think it's something very interesting because artificial intelligence is something wow, impressive. But so there are also even more modern ways to do that. And by the way, I'm thinking of that. Well, I'm talking to Mathieu, if he's here. Maybe for the RS3, it could be useful, more useful than for the low resolution spectroscope. But, we'll discuss that.
Okay.
Okay?
Yes.
François?
Yes?
David here. I have a question. Is the problem with fitting lines not very similar to plate solving in astrometry? And are there algorithms you could pick up from that?
Yeah. Well, this is a very good question. I think so. I think you are right. And I'm dreaming to find a still better way, more efficient way to find the matching. I think that you are right. I'm sure that this is the same system. This is even simpler than the plate solving, because you have only 1D data. And well, so far I've not found anybody able to work on that, and and that's it. And the point is that what we are doing is something in what we call in brute force. It works. So this is an intense calculation. We take all the combination. Well, not all of them. We don't take the extreme combinations, but really we do the thousands of calculations to get the results. And we say, I would love to have something more clever and that go directly to the right solution, like the plate solving does. And really, I think that the calculation behind should be the same. The point is that what we see today is when you look at the demonstration with the LP data, it just takes a few seconds. So it works. So, I mean, okay, so instead of taking 2 seconds, it will take half a second. It isn't worthwhile. It's not worth to spend the energy on that, you know, from practical system. And then I think that we have to put our efforts on other topics than this one. But I fully agree. If you find the solution, I will implement it.
Thanks, François.
That's it. We stop here, Olivier.
Yes, so just some more question, maybe. So not. So
no, that's it. Well, thank you very, very, very much for your attention. I hope it was useful. Again, I think it's, for me, the algorithm is here, the tool is here. Now, it doesn't mean that it is magic. This is just calculation. And I think it's really good to know what are the limits and what is the potential of this tool. And again, regarding Demetra, so we are still in a phase where we want to develop this software, and we are working on the LISA version, which will be released soon, I hope. And thanks to really to the wonderful job of Woody, Sean, Tony, and it is very impressive, and we will be ready to release this new version soon. Oh, sorry, I missed what I wanted to say. Well, there is, you are, even if we have a robust calculation, you are always responsible for the result and the data that you give to the communities. This is something which is very, very important for me. And we want to develop this software. And then if you have good ideas, if you have new needs, for some tools, anything, I want, and we want with Nicola, that this software evolve with your needs. So this is really, in my mind, a software that we want to give to the community. Okay, so if you have any question, please ask. And by the way, to finish on this workshop, if you have any suggestion of other subjects to talk for next workshops, it will be a pleasure to see what are your suggestions. Okay.
François, you might
Yes.
remind people of the videos on your website.
Thank you. Thank you, Woody. Yes, the organic. Well, I hope that most of people here know that, but for some time now we have made some tutorials, so video tutorials on Demetra, and I think this is really the best way to show how to use it. So we have now I think more than 12 tutorials in English and in French, and you can use it. This is the best way to learn Demetra, and you should have a lot of explanation for that. But I think that in this video, I have not been so deep in the calibration part, of course. Thank you, Woody.
Thank you,
That's
François. It was very informative. Thank you.
Thank you, David. Thank you. Well, take care. Take care, all of you. And we keep the contacts. And it's a pleasure to work with all of you. And now, please go to the sky and let's do wonderful science all together. Okay? Thank you very much. Bye-bye.
Merci. Au revoir.
Thank you.
Bye bye.